Okay, so we'll first do an overview on finite element, summarize what we've done up to this point, and then we'll go through another example. So recall that in a lot of engineering problems you have some idea on a governed equation. Here's one example, an ODE of this form is equal to some forcing function. So this could be a rod under a gravitational field, could be a heat transfer problem under some distributed thermal convection or heat generation. And we have a boundary condition of displacement or temperature on one end and a flux or a load on the other end. So this is valid over some length 0 to L. So instead of solving this directly, which sometimes this can be very complex, even in 1D, if this is this force is a complex function. So instead what we do is we satisfy the ODE, later we'll talk about PDEs, and boundary conditions in a weak or integral sense. So what I mean by that is we take the ODE here, we set it equal to 0 by pulling this to one side, and we multiply it times this weight function. So we solve it in a integral, weighted integral sense, where this is unknown, but we want to find a function here that makes this whole thing 0. So essentially this is what we sometimes refer to as a residual. So if we can solve this exactly, then this is always 0. But we find when we discretize it, there'll be some residual left. So this won't be exactly 0, but we want to try to get as close as possible to 0. So the discretization first starts with the true continuum. So a rod, you've got internal forces, you've got a load on the end. We discretize it into finite parts that are connected at nodes. So at each one of these nodes you've got an internal displacement or temperature, and you got an internal force or heat flux for heat transfer mechanics problems. So we approximate this true solution by nodal solutions at every one of these finite element nodes, and that is equal to this summation here. So these terms here, u sub j superscript e, where e is for each element, j is for summation of the number of nodes for each element. So in this case there's 2 nodes on every element, so n would be 2, and then you've got this polynomial function that we have to specify. So these are your unknowns. These become the vector components in this array, or this array U. Here's your matrix K. This comes out of the weak form of the ODE, so K comes out of here, and then F is whatever's left in here, and you may have natural boundary conditions inside Q. So once we have this, you have it in a form where you know either a set of flux or load boundary conditions, or you have a set of displacement boundary conditions, but not both. It should be unique, then you can invert K and you can find the displacements and the unknown loads. Now the final step in the finite element, and we haven't talked about it in great detail, is post-processing. So of course once you solve this at every discrete point, you want to be able to get the full field solution everywhere. So we take these discrete solutions in an array here, and then you can get things like strain, stress, flux, etc. by using these interpolation functions and of course our nodal solutions. For example, if you want to know strain, let's say, so a displacement gradient, these are constants, so you just differentiate this interpolation function and that'll give you strain everywhere. Or if this was temperature, you'd have a thermal gradient, you multiply that by conduction, this gives you heat transfer.